Good. So May 28th. And here is the adjustment to the syllabus. You know, I forgot to add this date here. That's going to be this meeting. That's going to be the last meeting before the final exam. It's going to be next Wednesday. Let's see. Next Wednesday, May 4th. May 4th, no, June 4th, okay? June 4th, and the final is going to be on June 9. So we're going to have 2 more meetings ahead of us, both meetings next week. We have 2 days meeting and 2 more meetings next week, plus the final, which is also considered a class meeting. Okay. And let me go to Canvas. Let me stop sharing the screen. And we have this. Let's see here what I have to do. Lab 6. Okay, let's not forget the report for Lab 6 is due today, right? Yeah, report for Lab 6 is due today at 11:59. I'm going to write down here my notes. For Lab 6 is due today at 11:59 p.m. And I need to upload the data for for today's report, which is Lab 7. Okay, and I also have to create something here in Canvas. The assignment. Let's see here. Load special assignment name Lab 07, lab report 07 due. Let's make it due on June 4th. It's going to be 100 points. I'll upload text entry. There's no need to restrict upload file types. Okay, so I'll allow it attempts until you have unlimited allowed attempts until the deadline. plagiarism review. Everyone. So let's save it. I'm not sharing the screen on purpose, okay? I'm not sharing the screen on purpose because I don't want to show the grades publicly here. Now, good. Let's see now if it works the way I want. Yeah, that's right. It works the way I can see here. Now, let me upload the spreadsheet. Data. This lab is the shorter lab compared to the other ones. The You want to say anything, Genesis? So I'm gonna mute Genesis. Looks like she left her mic on accidentally. Let me admit Justice. Go. Okay, I'm gonna take this chance here and let's upload your lab reports now. Okay. Okay, Leslie, you have your spreadsheet with your data. Oh, let's go for by alphabetical order, right? Here you go. Ahmad, you have your lab, have your spreadsheet there. Next is Nestor Alvarado. You have your spreadsheet there, Nestor. Just download it. Submit for student. 3. Isabella Ballesteros. Justus Bowden. Benjamin Carvajal. Elizabeth Castellano. Natalia Córdoba. Jacqueline Delgadillo. Jenny Diaz. More students coming in. Let's see, Jenny Diaz, you have your spreadsheet there. Valerie Diaz. Juan Escalera. Bianca Elocchi. Edwin Gonzalez. Ili Gonzalez. Manuel Hernandez. Samantha Hubbard. CJ. Amber Lopez. Arely. Mary. Galia. Jeremy Pittman. Okay, thank you. Check here. All the names that I'm calling is for the spreadsheet. Okay, so make sure you download your spreadsheet. Takes some time because we have lots of students in this class. 31 students. You have to figure out how to automate this task. I don't think there's a way to automate this task. Alexandra, you have your spreadsheet there. Jason is next in line here. Okay, so Hema. Okay, last but not least, Hema, right? So now I can let's take a look. Assignments, lab number 7. Okay, good. We have everything here. Okay, and let's start sharing the screen again. Good. So creation. No, that's not what I want. I want something else here. Syllabus, notes. I want lab slides. Why? Okay, this one is a good one, the better one. Yeah. And let's get the notes here on the screen. Lab 7. So um, please download spreadsheet for lab 7. Okay, so lab 7 is very similar to lab, let's see which one. Lab 7 is very similar to two resistors in series. This one is very similar to lab 5. Okay, with one interesting twist, one very interesting twist. Okay, lab 7, let's start lab 7. Lab 7 is very similar to lab 5. Okay, going back here in your notes, or can even be your syllabus. Okay, let's lab 4. Okay, very similar to lab 5. As a summary, lab 4. Lab 4 was a circuit with a single resistor. Lab 5 was a circuit with two resistors in series. Lab 6 was a circuit with two resistors in parallel. And now we're gonna go back to lab 4, lab 5. Right now, we will go back to lab 5. Here you go. Let's put it. Lab 7 is similar to lab 5 with an important difference. Okay, there's an important difference. We do, here you go. We still have two elements in series. We still have two elements in series. However, one of the elements is a ohmic resistor. When I mean an ohmic resistor, a regular resistor, okay? Your regular resistor. A regular resistor that obeys Ohm's law. But the second element is a flashlight bulb. Okay? Okay, a flashlight bulb also has a resistance. A flashlight bulb also has a resistance. But its resistance is not constant. It's not constant. But its resistance, let's put here, varies with the current in the circuit. Okay? In the circuit. All the resistors we have worked so far had a constant resistance with current. These are called ohmic elements. By the way, that's not in the book, okay? That's not in the book. So all the resistors we have worked so far had a constant resistance. The resistance did not vary with current, was constant, had a constant resistance with current. The so-called, let's here write that, the so-called ohmic elements are ohmic resistor, ohmic element, or ohmic resistor. However, not all resistors are constant with current. However, there are, let's put it another way. There are some elements, electrical elements out there whose resistance changes with the current. The so-called non-ohmic resistors. The flashlight bulb is one of them. Okay, and when I mean flashlight bulb, I mean when I say the flashlight bulb, I mean the regular one, not the LED light source, right? Which, by the way, which is a non-ohmic element as well, okay? Which is a non-ohmic element as well, okay? The flashlight bulb is made of those older light bulbs that have just a filament in there. The filament, when current passes through it, the filament glows and produces light, okay? There's a name for this type of light bulbs. I always forget it. It's always light bulbs. Let's see, light bulb. Let me see if I can get. See that's the type of light bulb I'm talking about. Is a filament here, and then incandescent light bulb. Okay, incandescent light bulb. The flashlight bulb is an incandescent. The flash light bulb is an incandescent light bulb. You know, the thing that brights up in your head when you have an idea, right? Have you ever had this sensation? Sometimes you're talking to someone and then you feel that a light bulb goes inside your head. They illustrate that in the comics, but that that's real life. Okay, I have felt something like that before when I was talking to my boss at my previous job. I was talking to him, and then that light came very bright inside my head. It happened to me only twice in my whole life. You know, we see those things so frequently in the comic books, right? But it doesn't happen with frequency in real life. It is as though as your neurons made the right connection in there, and suddenly you have this burst of current in your brain. That what might be. Okay, that's what might be. So flashlight bulb, okay, incandescent light bulb. Remember, is a non-ohmic element. A non. Again, let me repeat here. A non-ohmic element is an element whose resistance changes with the current. Changes with the current. Okay. In other words, the slope of the V versus I, the slope in the V versus I graph is varies. Okay, and that's what we're going to see today in this data. I'm gonna get my notes for the previous lab here, lab number 5, and then I'm gonna make just some small adjustments just to make my life easier. And I'm going to also to show you the slides. Lab 5, lab 5. Where is lab 5? Let's pick this one. Yeah, no, lab number 4. Lab number 5. Let's see if you can find it. No. Lab 5. Oh gosh, no. 4. Secrets. Monday, this one here. It takes me too long to find it. I'll just do that from scratch, from the top of my head. Wednesday, week number 11. Let's see. Can't find lab number 5 here. Strange. Okay, so I'll have to do that. Okay, let me do that from the top of my head. I can't find it for some reason, the notes. Okay, so we're going to start with, materials. Materials and procedure. Okay. The first material that you should be already familiar with is the multimeter, the digital multimeter. It's very important, this device. Okay, if you're going to do any work in electronics or electricity, you must have a digital multimeter. You must work with those things. And here's an illustration of one possible digital multimeter. Okay, a handheld device that fits in the palm of your hand, a little bit larger than the palm of your hand. You already saw one that I have, but there are larger devices like that, okay? And what else do you need? You need two. You're going to need a resistor, I'm gonna specify an ohmic resistor. Okay? And a flashlight bulb. Flashlight bulb is an incandescent light bulb. Okay? And then what you're going to do, procedure. Okay, we need one more thing here. We need a black cable with a banana terminal. And then a red cable with banana terminal. And also 2 alligator clips. 2 alligator clips. Okay? So, 1. Adjust your DMM. Here you go, digital multimeter DMM, comma DMM. Adjust your digital multimeter to measure resistance. Okay. Measure the resistance of your ohmic resistor. And how do we do that? Measure first, plug black cable, plug black cable on jack, on black jack, inside the black jack of the DMM. Okay. Plug red cable inside the red jack of the DMM. Here you go. Black cable plugged in the red jack, red cable plugged in the red jack, black cable plugged in the black jack. Okay. Clip alligator. Let's see. Clip the other end, the other ends of the cables at the extremities of the resistor using the two alligator clips, right? So here you go. Plug here, and here at the other end we have the alligator clip that's clipped at the end of the resistor. This case should be just resistor R1. Okay. And now it's time to show you the spreadsheet. Seven. Okay, let's get this one here. It's time for me to show your spreadsheet. Okay, so here you go. That's the value of the resistor number 1. And then there we have the resistor RB. You're going to measure the resistance of the resistor RB as well. Okay, and there is a special way of making this measurement in a light bulb. It's not obvious, okay? So let's see here. Let me get a better illustration of a better incandescent light bulb, so you can understand it. Here you go. Let's see. Yeah, depending on the light bulb. Let's see. Let's see if I can get a different one. Yeah, let's take a look at this one. This one is a good one. I like this one. Let's see if I can download it. Save image as. Download it. Going there. Incandescent light bulb, and here you go. The flashlight bulb looks just like that. It's smaller, right? But it looks just like that. We have this. What you have to know about the light bulb, incandescent light bulb, we have the filament, right? In this case, the tungsten filament. Tungsten is a metal. And we must have this enclosure as well to ensure that you do not have oxygen here inside. Okay? If you break the enclosure, then the filament oxidize more readily. Oxygen, it's very good at oxidizing this filament. And whenever you have oxygen in the atmosphere, once you raise the temperature of this filament, once you pass current through this filament, you raise its temperature, and at a high temperature, the filament is more readily oxidized. Okay. And how these light bulbs are built, right? We have, here go, one of the leads goes through the tip of the light bulb here, the electrical contact 11 that you see in this inside the light bulb, right? Pass through the filament, and then we close the circuit by connecting the other end at the the cap that surrounds the light bulb. What they don't say here, here you go, number 10. Yeah, well, yeah, they do say here, okay? So this thing is made of metal to conduct electricity, but this tip that you see right here is also made of metal. But you have to insulate this tip from this other region of the light bulb so that you don't have any short circuit. That's why you have this insulation device here separating the tip that you see right here from the body, from the, let's say, from the screw, right, of the light bulb. Okay? So we do have a dielectric device separating this metal from this other metal that you have here. So we insulate this wire, this lead of the wire from this other lead here. These other wires that you see here is nothing but just support wires. Okay, preferably they should be made of dielectric material. So the wire support wires, so the the filament doesn't sag, right? That's why we have the support wire right in here. So outline of the glass bulb is 1, low pressure inert gas. Okay, there's an inert gas here. It's either inert gas or a vacuum, preferably a gas that doesn't oxidize, right? So they put argon, neon, or nitrogen in there. But you can also put a vacuum here. And don't forget low pressure, right? Low pressure. Low pressure means almost a vacuum. Tungsten filament, contact wire number 4. Okay, that's one of the contact wires. Goes out of stem. Contact wire goes into stem. And support wires. Support wires, stem, glass mount 7. Yeah, okay, that's a. Is also, this stem is made of an insulated material. 9 is a cap. Okay. So when you're going to measure the resistance of this light bulb, you have to make sure that you're measuring the resistance between those 2 points here of the filament. Okay? And how do you do that? You cannot break the light bulb and put the probe there inside. Okay, but you can do something else. You can put the probe in contact with this tip, okay, which is in contact, in electrical contact with this end of the wire. This other wire here has almost negligible resistance. And the other probe of the multimeter, you touch right in here, okay? That's how you measure the resistance of the light bulb. And then you log the resistance of the light bulb right here. Don't forget to put the units, okay? So that's what I'm representing here. Let's see here. Here's the illustration of the light bulb, okay? Let me replace that R2 with the RB, okay? See that I put a halo around the bulb, right? And here you go. That's the wire that goes to the tip, and that's the wire that goes to the side, right? Maybe I should put like that, okay? Let me see how I can stretch it here. I don't like it. Looks like I have to put that upside down. Group, and let's move it upside down, okay? Yeah. The other black. Here you go. But remember, this resistance is going to change as I pass currents through this device. When no current passes, we measure the resistance of this light bulb, okay? Measure the resistance of the resistor and used the resistances of the resistor and light bulb used. That's what we're doing, okay? And then we start with the circuit, put together the circuit. After measuring the resistance, we start with the circuit. We start with the power supply. Going back here. Put the power supply here. Power supply. And I'm going to need another cable, two. So that's two black cables, two red cables, two red cables. This banana terminal, power supply. Okay. Plug with the power supply. Plug black cable into the, just like we did with the multimeter, plug back cable into the black jack of the power supply. Okay, right in here. Oh, I put the red one. Doesn't matter. Plug red cable into the red jack of the power supply. I didn't turn on the power supply yet. Okay. Connect one end of the resistor to the red cable. Okay. The red cable using the alligator clip. Connect, let's see. You know what? I gotta put something else with the power supply. Connect the flashlight bulb in series with the resistor. You know what? Let's put this one before this other one here. Okay. Connect the flashlight bulb in series with the resistor using the proto board. And now protoboard. And now I can add here to the list of materials the protoboard. Protoboard. Connect the flashlight bulb in series with the resistor using the protoboard. And that's the protoboard right in here. Okay, and then I'm gonna put this one. That's a better place to put it. That's a better place to put it. Okay. You can see that this wire is connected in this row of the protoboard, which is making contact, electrical contact with the end of the light bulb, one of the ends of the light bulb. Okay, and now we can connect the red cable of the power supply to one of the ends of the resistor. Okay. Since this resistor is already connected in series with the light bulb, okay, now we can close the circuit with the black cable at the other end of the flashlight bulb. Okay, so here we go. Connect one end of the resistor to the red cable using the alligator clip. Connect the black cable. The black cable. Getting hot here for me. Black cable to the other end of the flashlight bulb. Flashlight bulb. Flashlight bulb, okay? And now we have our circuit, and then we can turn on power supply and set it to 10 volts. Set it to 10 volts. 1040 and set it to 10 volts. Here we go. 10 volts right in here, and that's how the circuit looks like. Very similar to the other circuit. The only difference is that we replace the resistor 2 with the light bulb. Okay. Here's the filament, right? Here's one of the leads of the filament. Connect to the filament. Another lead connect to the filament. Let's see if I can get this thing. Make it nicer. Make it bigger. And what else we have to do? When I get the multimeter now, we already have 2 black cables and 2 red cables. Okay. So circuit is ready for measurements. All right. Now, with the DMM, first connect the DMM in series with both resistor 1 and the light bulb. Okay. With the DMM, one, adjust it to measure voltage. Set it, not adjust it, set it to measure voltage. Set it to measure voltage. Okay. Connect red red cable between red plug of the EMM and the first end of the first resistor of the resistor. Connect black cable between black plug of the DMM and the other end of the flashlight bulb. Flashlight bulb. Here you go. Flashlight bulb. That's what we have here. We're going to measure the electric potential between those two ends, just like we did before, right? And now we're ready to take more measurements, and we can go to the spreadsheet here, set the voltage is already set at 10 ohms, at 10 volts, right? 10 volts, and then let me put it here. Here's my yellow data, right? And here you go. Here's the voltage made with the multimeter and the voltage displayed in the power supply. Okay? That's what it is. So log voltage displayed in the screen of the power supply, and then log voltage displayed in the screen of the DMM. Okay. And then what to do next? Lower voltage to 8 volts in the power supply. I'd readjust, right? Let's put readjust voltage to 8 voltage in the power supply. And repeat steps for D and for E. Okay. Repeat step for F for 6 for 2.7, okay, volts. Okay, switch polarities of the power supply and repeat the steps. Set it, measure voltage with the DMM, okay, and repeat the steps for 10, 8, 6, 4, and 2.7 volts. Okay, and the drawing is this one right here. And when you do that, you should read negative voltage. I'm switching the polarity, right? And those, okay, here you go. Here the data for positive volts, right? Here's the reading in the multimeter for positive volts. Switch the polarity, you're going to get readings that are the negative of the voltage displayed by the power supply, and your multimeter is going to display an actual negative number. Okay, 1044. I think that's a good place to stop. Do you have any questions? Okay. So let's take our break now. And it's 10:45 right now. We have, I'll take attendance later on. Oh, wait a minute, let me take attendance. Let me take attendance since I have been doing that. P07, P38, here you go. Edwin's coming on. There are one more circular reference. Okay, that's good. P07 lecture, P07 lab. Now, today is the 28th. Ah, I didn't put it here. Okay. Let's insert 28 L7, right? L7. Let me take this one out here so I don't mix up. Clear. Abir, Ahmad, are you there? I see Abir here logged in. Let's go for the next one. Nestor Alvarado, are you there, Nestor? I don't see Nestor here. Okay, next is Monte. Just joined us, right, Monte? Hello, Monte. Monte is not answering. I'm gonna put a star here under his name. Isabella Ballestero. I don't see Isabella either. Next is going to be Justus. Hello, Justus.
Yeah.
Okay, so here you go. I just lost my connection here momentarily. Okay. So didn't used to do that. I was living in another place that didn't used to give me this type of problems. Here you go. Let me share the screen. Okay, good. So let's see. Justus, are you there? I can't hear. I don't hear from Justus. Oh, okay, good. Thank you, Justus. And next is going to be Benjamin Carvajal. Thank you, Benjamin. Elizabeth Castellano.
Here.
Thank you, Elizabeth. Natalia Cordoba. Thank you, Abir. What about Natalia? Natalia is here, is in front of her computer. Oh, here you go. Thank you. Thank you, Natalia. Thank you. Next, Jacqueline Delgadillo. Are you there, Jacqueline? Thank you. Jenny Diaz.
Here.
Thank you, Jenny. Valerie Diaz.
Here.
Next is Juan Escalera. I don't have one here. Let's see. Yeah, I don't see one here. Okay. Next is going to be Bianca Elwaki.
I'm here.
Thank you, Bianca. Edwin Gonzalez.
I'm here.
Thank you, Edwin. Ili Gonzalez.
Here, Professor.
Thank you. Manuel Hernandez.
Here, Professor.
Thank you. Samantha Hubert.
I'm here.
Thank you. CJ. Are you there, CJ? Okay, I'm gonna put a star under his name. And Amber Lopez. I don't see Amber, huh? Yeah, Amber doesn't look like she's here. Next is Adelie Lopez. Thank you. Next is Genesis Lopez.
Here.
Thank you. Mary Michaelian.
Here.
Thank you. Next is Galia. Galia, right? Or Galia. Don't know what's the right here. Okay, thank you. Ramon Olivares.
Here.
Thank you, Ramon. Okay, CJ. CJ Houghton. Okay, good. Next is Taylor Forn.
I'm here.
Thank you, Taylor. Jeremy Pittman. Jeremy is not here. Next is Stephanie Ramos. Stephanie, I don't see Stephanie in my list. Leslie Rios. Thank you. And Alexandra Romanov. Next is Jason Strait.
Here.
Thank you. And last but not least, Hema Torres. Hema, it looks like Hema is away from her computer. Let's see, Stephanie.
I'm here.
Hema?
Or did you say Hema? Sorry.
Okay, good. I got it. And let's see, who just joined us? Stephanie, right?
Yes.
Yeah, Stephanie. What's your last name? Stephanie Ramos, right?
Yes.
Okay, good. So let's see here if I have all the numbers right. 25 and who didn't answer? It looks like okay, yeah. There's some people who didn't answer. Let's see, 25, 26. Good. Monte, can you hear me, Monte? Are you there? Okay, Monte is not answering. Let's go for.
I'm here.
Oh, okay, good. Now Monte is answering. Let's take our break, 15 minutes break. It's 10:52 a.m. to 11:07 a.m. Okay, and I see you in 15 minutes. Let's resume recording and share the screen. And okay, so we got all the data that we want for the total voltage, and now we have to repeat for the voltage across the resistance and the voltage across the bulb. Okay, so the steps are similar. It's just repeating what we did before, but changing the connections of the multimeter, right? If you want to know V1, I have to connect the multimeter to this black, right, lead of the multimeter. I have to connect it here. Okay, so here we go. Okay, so here you go. The voltage across the bulb and the voltage across the resistor. Okay, the resistor here. Benjamin Cabajal, here you go. So the instructions are the same, and I'm going to highlight what is data and what is result. Okay, we're measuring. Let me put that here. Repeat. Another student. Repeat voltage measurements for the DMM connected in parallel with resistor 1. Repeat voltage measurement for DMM connecting parallel with light bulb, with flashlight bulb. And now, let me organize that. Circuit is ready for measurement. Measuring, let's put here measuring voltage with the DMM, okay? And now measuring current with the DMM. One, two, three. Adjust. Okay. Now we have to start from scratch. Disconnect everything and start from scratch. Disconnect everything and start from scratch. Okay. Power supply. Connect red cable to red jack of the power supply. And I'm going to illustrate that right in here. Here you go. Okay, and but now we have to connect the other end of the powers of the cable to the jack that measures current in the multimeter. Okay, many multimeters out there, they give a different color to the jack of the current. Okay, in this case here we have a multimeter there at the college that the jack of the current is yellow. Okay, so connect red cable to red jack of the power supply. Connect other end of the red cable to the jack of the DMM used to measure current. Yeah. And don't forget, measuring current with the DMM. The first thing that you have to do, by the way, adjust, okay, DMM to measure current. And then you connect it to the circuit. First adjust it, and then you connect to the circuit. Connect other end of the red cable to the jack of the DMM used to measure current. Okay, the DMM will be in series. The DMM will be connected in series to the circuit this time. Going back here, okay? Black cable to the black jack of the DMM. Black cable to the black jack of the DMM. And now connected to the resistors that are in series, right? Resistor and the light bulb, and you close the circuit. And the other end of the black cable connected to the near lead of the resistor. Okay, near lead of the resistor using the alligator clip. and the other end of the light bulb connected to the black jack of the power supply. The circuit is closed. The circuit is closed. And we are ready to make measurements. So here go. We close. Here you go. Circuit is ready. And now notice that the multimeter is in series with the whole circuit. Okay. And now, what do? You change the voltage from 10 to 2.7, right? Change the voltage of the power supply from 10 volts to 2.7 volts and measure the current. Okay. Invert the polarity of the cables going to the power supply, and repeat the current measurement. Okay. And here go, inverter, right? And then we are done collecting the data, and now we collected all. And when you do that, you're going to see that when you invert the polarity, you're going to see that the measurement of the multimeter is going to be negative. So here you go. Here's the last set of measurements. Those two are measurements. Keep them yellow, right? Everything else here are going to be results. Everything else here are going to be results. This one is what? V1 plus V bulb. Okay, so this V1 plus V bulb is going to be very similar to this measurement. This result here is going to be very similar to this measurement that we made. And let's highlight it with which color I'm going to use? Let's, okay, orange color. Okay. To distinguish actual measurements from the results. And then what you're going to do? We're done with the experimental. Done with the experimental part. Now we will analyze the data. And all you have to do, plot V bulb versus I. And let's plot the other one too. Plot V1 versus I. Subscript. V1 is the measurement done with the resistor, right? Which is an ohmic element. So let's plot V1 versus I first, and then we plot the other one. And let's see if it works. Here go V1 versus I. Insert chart. Here you go. You can see that because the resistor 1 is an ohmic element, you can see that the relationship between V and I is linear, right? And of course, you gotta put the add trend line here. Display. Okay. Two graphs. Let's make it two graphs. And then the next graph we want to plot is V of the bulb versus I. of the bulb versus eye. So let's see what we get. Remember, it's not a straight line. It's not a straight line because we do not have an ohmic element. Okay, this guy here behaves like a polynomial. A polynomial of third degrees is not even a polynomial of second degree, okay? It's a polynomial of third degree. A polynomial of third degree has this type of behavior, a hyperbola. So let's, click on one of the data points, right click, add trend line, and we are going to display, okay, polynomial. Instead of linear, you're going to click on polynomial, okay? And use order tree, okay? If you try to put a linear, let's see, if you do a linear regression, right? You get this straight line that doesn't coincide with the data points. If you do not a linear regression, but a parabolic regression, right? Let's see if it does. Yeah, I don't see. Yeah, it doesn't change much, right? But if do a third order polynomial regression, here you go, polynomial here, and increase the order to not to 3, now we have a curve fit that is much closer to the data points, okay? That was the first, that was the linear regression, right? Now I'm going to erase it from here. And we want also to display the equation chart and display the R-square value. See here, Microsoft Word, Microsoft Excel is smart enough to calculate this equation. It's not easy to calculate this equation, okay? It's much easier to do the first order, the linear regression, but the third order regression is more difficult, and other types of fitting curve. Okay. Now let's see if you're doing well there, and I'm gonna call you one by one now. Any questions about that? I wanna know if you downloaded the spreadsheet first, right? And then plot G1, plot G2. And after plotting G1, let me know what is the slope. Okay, the slope of your graph. Don't forget the trend line. Make sure you get a trend line. Let's start with Abir. Did you download your spreadsheet, Abir? Hello, Abir.
Yes.
Yeah, you did download. Okay. Did you plot your first graph?
I'm doing it right now.
You're doing right now, working, right? Working on that. Nestor Alvarado, are you there, Nestor? No, Nestor didn't come in. Next is Monte. Did you download your spreadsheet, Monte? Monte and Barchelin. What happened to Monte? Looks like he left. Yeah, looks like he left. So Nestor, yeah. Next, Isabella. Are you there, Isabella? No, doesn't look like. Justus Bolden, are you there, Justus? Hello, Justus. Looks like Justus is not in front of the computer. Let's go for the next one. Benjamin Carvajal. Did you download your spreadsheet, Benjamin? Okay, good. Did you plot the first graph? Yes. What is the slope that you got? What is the slope that you got for the first graph? And okay, Justus downloaded. Okay, I'll get back to you. Benjamin is 78, right? 78. And does it make sense, Justus? What's the value of your resistor, by the way? 782, right? 78, 782. What's the value of your resistor, Benjamin? Hello, Benjamin. Let's see, what's the spreadsheet from Benjamin? Let's see here. Okay, I'll get back to you. Okay, if you're not ready to tell me what's the resistance value of your resistor one, I'll get back to you later on. Now let's see, Justus, did you plot your first graph? For the plot, yes. What's the slope that you got? What's the slope that you got for the first graph? 67.45. What is the value of your resistor number one in the first table? This value right in here in this cell, okay? In my case, it's 81.3, right? What about yours? What's the number that's typed in there? My slope, let me check. Yeah, just click the cell and read the number here in the window that's upstairs. Yeah, and also what's your group number for the spreadsheet, Justus? Group one? Okay. So let's see here. Copies. Group one. No, I don't think it's group one. I think it's something else. Okay. Okay, so let me go to the next student. Elizabeth, did you download your spreadsheet? Yes, it's working on the first. You're working on the first graph. Okay, good. So let's go to the next one. Natalia, did you download your spreadsheet? Okay, downloading or working on the downloading. Okay. Jacqueline, did you download your spreadsheet? Yes, that's good. And did you plot the first graph? Not yet, working on that. Okay, good. So let's go to the next student, Jenny. Jenny Diaz, did you download your spreadsheet?
Yes.
Okay, did you plot your first graph?
Yes.
What's the slope that you got?
92.403.
Okay, 0.403. And what is the value of your resistor there in the spreadsheet? R1.
It's 91.04.
91.04. Okay, so it's close enough, right? 91.04 is very close to 92.403, right? That's how and your graph is a straight line. That's how ohmic elements behave in terms of the resistance. Now, did you plot the second graph?
Yes.
Okay, and what's the trend line? Did you fit your trend line there to the third power?
Yes.
Okay, so did you get something just like I got here? Not this one, but this one, right? See that?
Yes.
Yeah, okay. So now do you see you do not get a straight line. You do not get a straight line because the light bulb is not an ohmic element. Okay? So we do have elements that don't behave linearly with the current. The voltage versus current graph doesn't go linearly, okay? So okay, it's group 6, right, Justice? Okay, thank you. Okay, so continue working on the rest. Okay, Jenny, right? That I'm talking to.
Yeah.
Okay.
Okay.
So the trend line. What else? You got units, right? Work on the units. Sig figs. Sig figs and the second table. Second table. Let's see. Next is gonna be Valerie. Hi, Valerie. Okay.
Hello.
Okay. So let me see here. Okay. So did you download your spreadsheet, Valerie?
Yes.
Okay. Good. Did you plot your first graph?
Yes.
Did you get the slope of your first graph?
Yes.
Okay. How much is that? What's the value?
85.258.
2.5. Okay. Good. Now let me put another thing here. Tell me where's the resistor, the value of your resistor 1 there in the spreadsheet, in that cell.
90.85.
90.85, right? What's your group number there in the
3.
spreadsheet? 3? Okay, so let me see here. A little bit far off, 5% difference seems a little bit too much. Let me see. Group number 3. Copies. This one. Yeah, here you go. 90.85, right? And then you plot V1 and I. Let's see. Add trend line, display equation chart. Yeah, that's right. It's a 5% difference. It's not common to get this big difference in this type of experiment. But yeah, okay, we got the right numbers. And now I want you to plot the second graph, right?
Okay, I did.
You already did?
Mm-hmm.
Okay. So did you get the trend line in terms of the
Yes.
polynomial third power?
Mm-hmm.
Okay, so let's see. Let me get another. Get me the. What's your R square?
0.9978.
0.9978. 0.997. Okay, that's a good R square. Plotted the R. Okay. Now you can work on the units. Okay.
I did the units.
Significant figures. What did you say?
I already did the units. I just have to do the sig figs now.
Okay, good. Sig figs is more work, right?
Mm-hmm.
Number 3. Let me put everybody's group number here, so it's easier for me to refer. You said that your group is number 6, right? Yes. Okay. Good. And Valerie's number 3, and 6. And did you find out what's the value of R1 there, or Justus in the cell for the R1? $65.05. Okay, $65.05. So you can see that those two values are rather close to each other. I would say almost 4% difference. Okay. Here is a little bit more than 5% difference, but it's small enough. Okay. And go ahead, plot G2, second graph. Did you plot second graph? You're working. Okay. Okay, so we'll work on the trend line of the second graph. Let's go for Juan. Juan Escalera, what's your group number there in the spreadsheet? Group one is not here, right? Juan Escalera is not here. Yeah. Next is Bianca. Bianca Eloki. I'm downloaded, working on graph. I'm group 4. That's good. Which group? You're working on the first graph. Is that right, Bianca? Yes. Okay, good. Now, next. Oh, did I get the wrong one? I put in the wrong one. Yeah. 4. Working. Here you go. Next. Downloaded. Next is Edwin Gonzalez. Hello, Edwin. I don't see Edwin here. Looks like he left. Put a 0 here. Oh, Eli Gonzalez.
Yes, I have done both graphs. I have the slope, the R1, the R squared, sorry. I've done units and sig figs already.
Okay, what's your group number first?
8.
Which one?
8.
8? Okay, good.
Ocho. See.
Yeah. Okay, so you downloaded, you plot graph 1. What's
Yep.
this? What's the slope that you got?
The slope is 80.40, and my
Okay.
resistor number 1 is 80.50.
8.5. Wow, this one is, wow, let's see, is 1 in 100. So it's a little bit more than 1%. No, it's less, much less than 1%. It's like 0.1% difference, a little bit more than 0.1% difference. Okay, that. And did you plot graph number 2?
Yes.
Okay, were you able to fit the hyperbole there to the graph?
Yes.
Okay, good. What's the R squared that you said that I didn't pick up before?
0.9970.
70. That's good. And now, yeah, go ahead. Good.
Yes and yes.
Okay, so you finish units and sig figs?
Yes.
Okay, good. So, yeah, what about the second table?
Table's done.
Oh,
Second table.
yeah, that's right. This table here, right? After the first one. No, actually the third table, right? That's the first table, that's the second, that's the third one.
Oh, okay. I'm working on that right now.
Okay, thank you.
Thank you.
Okay, next is Manuel Hernandez.
I downloaded it, but I'm still working on the first graph because my Excel's being weird right now.
Okay, what's your group number there in your spreadsheet?
Let me double check.
I believe it's 9. I believe.
Yeah, I think it is 9.
Okay, good. Good, thank you. What about Samantha? Let's go for Samantha.
Yes, I downloaded it.
What's your group number there in the spreadsheet?
Number 1?
Number 1?
Yep.
Okay, so you downloaded. Did you plot the graph number 1?
Yes.
Okay, what's the slope you got?
97.402.
Or, okay, 97. You said 97?
Yes.
0.402. Okay.
Yes.
And what is your resistor value in that cell upwards there?
92.26.
Okay, 92.26. We're talking about 5% difference. Maybe we are getting this difference because of the effects, nonlinear effects of the light bulb. That's a possibility. Okay.
Okay.
And did you plot the second graph?
Yes.
Okay. Were you able to get the trend line for
Yes.
Okay, that's good. What's the R square that you're getting there?
0.9967.
6.7. Okay, so that's a very good fit. Like I said, you're never gonna get one. Okay, if
Yeah.
if you get one, there must be something wrong there. Okay.
Okay.
And did you finish the units already?
I'm working on that.
Okay, working on the units. That's good. Let's go for CJ. Are you there, CJ? I can't hear. Still working on the spreadsheet. No change. I got to do 6 figs. Okay, so you cannot hear me. That's what he said, right? Okay, so I will skip you for now, and let's see. I think it's my headphones. Okay. Okay, so yeah, check your headphones there. Let's go for the next one. Amber, are you there, Amber? Amber doesn't look like Amber is here. Next is Arely Lopez.
Yes. I was able to download the spreadsheet. I was just having trouble downloading it, and right
Uh-huh.
now I'm working on my first graph.
Okay. Do you know what's the group number in your spreadsheet?
Yes, it's group number 5.
5. Okay. Thank you. Let's go for Genesis. Can you hear me, Genesis? It doesn't look like Genesis here. Okay, Genesis left. And Mary, can you hear me? Let me switch this one here. Cut. Okay, are you there again, Mary? Okay, I'm gonna put a star here on Mary's name. Galia, are you there? Can you hear me? Doesn't look like Galia is here. Okay. Next, Ramon Olivares. Ramon is not here either. Taylor?
Yeah, I downloaded my spreadsheet.
Okay. And what's your group number there in the spreadsheet?
1.
1. Okay. Do you plot the first graph?
Yes.
What's the slope that you got?
97.402.
Yeah. Okay. And what is the resistance, the first resistor that you got there?
92.26.
Okay. So just like the other is 5% difference, right? Did you plot the second graph?
Yes.
Okay. Did you get the trend line as well?
Yes.
Okay. So you use the third order polynomial for the trend line, right?
Mm-hmm.
What's the R square value that you're getting?
0.9967.
9967. Okay. Group 1. Yeah. Good. Did you work on the units already?
I'm working on that right now.
Okay, good. Thank you. Let's go. Jeremy is not here, right? Stephanie Ramos. Are you there, Stephanie?
Yes, I downloaded it. I'm working on the first graph, but I don't have access to my laptop today. So when I'm doing Excel, I'm doing it on my iPad. So it's not working like to graph it.
Uh-huh.
Just because I don't have access today with my laptop. But I am following like what you guys are doing and everything.
Okay, good. So what's your group number, please, in your
I
spreadsheet?
think it says number 3.
Number 3, right? Okay, good. Thank you.
Okay, thank you.
So if I have time, I'll go back to you. Let's go here to Leslie. One more minute and we will take a break, okay? Are you there, Leslie? Okay, group one, thank you. Did you download your, yeah, you download your spreadsheet. Did you plot your first graph? Yes, that's good. What's the slope that you got? $97.402. Okay, good. And what is the value of your resistor there in the spreadsheet? In the cell at the top? 92.26, right? That's good. Okay, very small percentage difference again. Did you plot the second graph? I'm working on G2. Okay, working on G2. That's good. And 11:45, I want to have another break now. Okay, I'll get back to you once we are after the break. Okay, Mary? But let me just log in here, 7, group 7. Okay, and you understand you're able to download it. And let's have our break now. Break 11:45 a.m. to 12 noon. Okay, and I see you in 15 minutes. I am back here. Okay, so let's. Oh, my. Now let me get something here too. Okay, just get more comfortable here. Let's go back to our spreadsheet here. Not this one. This one here? Yeah, this one here. Now, let's see. Alexandra, your turn now. Alexandra, are you there? Okay, I'm working on the first graph. Okay, so you're able to download the spreadsheet. Which group number are you, by the way, Alexandra? 5? Okay. And so working on the plot of the first graph, right? Okay. So let's go to JSON straight.
Yeah, I downloaded it. I'm working on the first graph.
Okay, what's your group number there in the spreadsheet?
6.
6, okay.
I did do the other graph though.
Oh, you did do the other graph. Okay.
Yeah, I did the first one. Not the first one, but I did the second one.
The second one, right? And you got the trend line, right?
Yeah.
What is this, the square root or the R square?
For graph 2, I got 0.9971.
7, okay, that's good. Okay, finish the first one and double check your, double check your slope with the result of your measurement, right? With the measurement of your resistance. Okay, let's go to Hema now. Are you there, Hema? Okay, just download the Excel spreadsheet and group 7. Okay. So you're still working on on the graph number 1, right? Okay, so let's see. Oh, Mary, right, Mary? So you're group number 7. And you plot graph number 1, Hema? Mary? Let's see, Mary's here. No, Mary's not here. She left. Okay, so let's put here 0 and okay, Abir, were you able to plot graph 1? Is Abir there?
Yes.
Okay, so you did plot 1. What is
Yes.
what's your group number there in the spreadsheet, please?
I'm sorry?
Group number in the spreadsheet, G0 whatever, right?
Yes, it's gonna be 4.
4, okay, good. So this slope, did you get the slope for the
My
graph?
slope? Yes, it's gonna be 82.423.
0.42, okay, that's enough. And what's the value of your resistance 1?
That I have not gotten yet.
Okay, it's just all you have to do is it's straightforward. Okay, all you have to do is to click your mouse in the cell J4. Okay, column J, row 4. Do you see here in my, if you click it here and then you read here at the top. In my case, it's 90.85. Okay, can you do that? Click and then you consult there at the top left of your spreadsheet the numeric value of this resistor. Okay. Did you do anything else, Amir? Other than the...
I'm still working on the rest.
Okay.
Oh, I did plot the second one. I did plot the second.
You did plot the second one. Okay, so you got the trend lines for the second one. Okay. No questions about that. See the...
No.
Okay. It's R square. What's the R square you got?
I have 0.9976.
76. Okay. Did you work on the units already of the table?
I'm still working on units.
Okay, good. Okay, I'll get back to you later on. Let's see. Nestor Alvarado, are you there? No. Monte Ambarchian. Monte, no. Nestor, Monte. Isabella Ballesteros. I don't see Isabella either. Let's see. Justus. Are you there, Justus? Okay, I got trend line as well, R square. You're talking about the trend for graph number 2, right, Justus? Yeah, okay. So trend line 0.9966, 0.9966. Okay, did you work on the units already? Yes, working on the 6. Okay, you're working on the 6. That's good. Okay, so if you have time, I get back to you. That's next one here is Benjamin Carvajal. Hello, Benjamin. Group 7, thank you. R1 was 80.18, right? 80.18. So you're getting maybe 2 or 3% difference between the slope, the experimental value, right? And your result. Experimental value is the R1 that you measure with the multimeter. The result is the slope value of your graph. Now, did you plot graph number 2? Yes. What about the trend line? Did you manage to fit the cubic trend line there? Good. What's the R square that you're getting? .9957. Good. Did you work on the units already? Working on it. That's good. Okay, working on the units. That's good. Next is Elizabeth Castellano. Elizabeth here.
I'm in group 8.
Your group number?
8?
8. Okay. 8. Did you finish plot of graph 1?
Yes.
Okay. What's the slope that you got?
80.3.
80.3. And what's the value of your resistor number 1?
My resistor 1 was 80.5.
80.5. Okay. 80.5 group number. Yeah, just like Ely, right? Just like Ely here. Good. So this is good data, right? Because it's very small percentage difference. Did you plot graph number 2?
Yes.
Yes. Did you see the trend line there?
Yes.
Third order polynomial. What R squared that you're getting?
My R squared was 0.997.
0.99. What else?
997.
997. Okay, good. Did you work on the units as well?
I'm working on them right now.
Okay, that's good. So let's go to Natalia right now. Did you download Natalia Cordoba? Did you download your spreadsheet? Let's see. Natalia doesn't look like she's here. Okay, so next, Jacqueline Delgadillo. Okay, what's your group number, Jacqueline? Group number 1. Okay. Did you finish? Okay, you finish graph 1. You got the slope 97.6 and R1 is 92.3. That's good. 92, 5% difference. A little bit more than 5, right? You plot graph number 2. Did you plot graph number 2? Nope. Okay, so I'm gonna put that you're working on that. Okay, so do you need any help with graph number 2, Jacqueline? Okay, I presume that you don't need any help, right? So let's go for Jenny Diaz. Jenny, last time you told me that, let me know what's your group number, Jenny. Let's see if Jenny's here.
2.
2, okay, good. Did you see did you check the value for the resistor number 1?
Yeah.
What's that?
It's 91.04.
04, okay. So we're talking about a little bit more than, yeah, 1%. 1% difference between those two. Maybe a little bit more. Okay, did you plot the graph number 2? Yes, you did plot, right? Did you get the
Yes.
trend line for graph number 2?
Yes.
Okay, and the R square as well?
Yes.
What was that?
It's 0.9977.
9977. Okay, good. And what about your units? Did you work on that?
Yes.
Okay, you finished. Okay, and what about the sig figs?
Yes.
You finished it? Okay, good. And the second table?
Yes.
Okay, so you're done, right? There's nothing else. You
Yeah.
finished everything. Okay, that's good. If you can, if you can help some other students, that would be would appreciate. Okay, so let's go for Juan Salvador Escalera. Is not here, right? Escalera is not here. Next one is Bianca Oloki. Bianca left. Oloki, yeah, next. Edwin Gonzalez. I don't see Edwin here. Next, Eli Gonzalez, you finish everything, right? The only thing that you haven't done was the second table. Eli, did you manage to finish?
Yes, and I completed that table.
Okay, that's good. So, do you have any questions?
Nope. Nope.
Okay. Okay, that's good. Okay, let's go for someone else here in the line, in the list. Manuel
I'm still
Hernandez.
working on the first graph. I think I have to restart my computer because my Excel is not working right now.
Okay. Yes, if you can fix that, okay. And let's see, Samantha.
I finished the units. I'm working on the sig figs.
Okay, the sig figs take a little bit longer, right?
Mhm.
Let me know if you need any help. CJ, are you there, CJ? CJ has a problem with his speaker, right? Problem with the speaker. Let's see here. With speaker. Okay, now let's see. Amber Lopez. It's not here. Next is Adelie. Are you there? I don't hear from Adelie. Okay, so I'm gonna put that star here under her name. Next is Genesis. Genesis is not here. She left. Let's see, Mary. Mary. Looks like Mary left. Okay. And Galia. Okay, Galia is not here either. Ramon Olivares. Oh, Ramon is not here. Let's see, who is that? Taylor. Hi, Taylor. Let's start.
I finished the units. I'm just working on the sig figs.
Okay, good. Six figs take some time, right? A long time. Okay, what about Jeremy is not here. Next is Leslie Rios. Hi, Leslie, are you there? Okay, Leslie's not answering. Let's put a star here in her name. Alexandra Romanov. Alexandra Romanov. Okay, let's start working on graph 2. Okay. Graph 2. So you finish, so you finish graph 1, right? Alexander? Yes, okay, good. What's the slope that you got for graph 1? Double check, please. Okay, so around 97.2. Okay, 97.2. What about the value of your resistor in that cell J4, right? Can you check that for me? J4, this guy right in here. You click in this cell, and then you read the number there at the top. Okay, you can tell me later on. So let me move forward with another student, Jason. Jason Straight. Hello, Jason.
Okay. So I finished graph 1.
Uh-huh.
I got 82.544 as my slope.
Oh, 82. Let's see. 82.54.
Yeah, 544.
Okay, 544. Okay, can live like that. And what's the resistor value?
81.3.
81.3. 81.3 is 1%. 1% difference, a little bit more than 1%. That's good. And you finish plotting graph number 2, right?
Yes.
You got the trend line, you got R square. What about the units?
The units, yes, I got them all.
Oh, you got them all. Okay, you finished. What about the sig figs?
I believe I got them all.
You got them all too? Okay, and it's not the second table, it's the third table. Did you work on the third table as well?
I'm finishing that up right now, so working on it.
Okay, good. Thank you. And okay, I'll give you a little bit more of time. 12:20, still have half an hour to go. So don't forget, we are getting at the end of the semester, right? Here you go. We are writing here on Wednesday. We still have 2 more meetings before the final exam. 2nd of June and 4th of June. And I plan to do a little bit more of special relativity. Since we have 20 more minutes, let us cover special relativity now. I think you can finish this lab report on your own, right? Unless you have any questions. And so hopefully we'll be able to finish this topic, which is relativity. See this one. Special relativity. And let's see what that we did. Let's go to the book as well. Okay, we're doing the energy, kinetic energy, and the mass energy, energy associated with the mass. Okay, and let's go also to the book. Wiley plus. And this one here, chapter 28. Okay, equivalence of mass energy, relativistic addition. Okay, yeah, that's what we did. Let's say events and initial frames of reference. Inertial frames of reference, we did it. Postulate of special relativity, we did it. Relativity of time, it's time dilation. We worked on that. Length contraction, we also worked it. We proved that by using the phenomenon of time dilation. Relativistic momentum, what you have to know about relativistic momentum is that you have a gamma factor multiplying the Newtonian momentum. That's what is a gamma mv, right? And where gamma is 1 divided by the square root of this equation here, 1 minus v squared over c squared. Equivalence of mass and energies was the last thing that we did. And now we're going to look at this relativistic addition of motion. Okay? And relativistic addition of velocities, not addition of motion, addition of velocities. So that's an important difference between Newtonian mechanics and relativity. Okay. We have, let me get my notes here first before we continue. I'm going to copy and paste. Here are the topics of chapter 28. Okay, we're going to cover everything. And okay, so we're done with kinetic energy and the energy of a mass. So what we're going to do now is, just remember what we did in relative motion during physics 06. Okay. Okay, in my class, the way that I do relative motion, I display to you two different referentials, one moving with respect to another. So let's say referential A is the ground referential, okay, that is at rest with respect to us. And referential B, let's say, is a car. It's a car that's in motion with constant velocity. And here's the notation that I'm using here. Velocity of B with respect to referential A. Velocity of referential B with respect to referential A. Okay? And I label the axis X and Y for A, X prime and Y prime for B. That's how I label them. Okay? And in physics 6, what do you do, right? You go, consider here two referentials. I have to introduce that to you so you can understand the difference between relative motion in Newtonian physics and relative motion in special relativity. Consider two referentials A and B. Okay? B, A, comma, A at rest with respect to us, and B moving with constant velocity with respect to A, right? With respect to A. So let's say here, so now let's add a point P to this, that both observer in both referentials are observing. Okay, in addition to these two referentials, we also have a point P somewhere in space. The point P can be, for instance, an airplane that the other two observers in referential A and B are observing. Okay, as an example, can be, and it's moving on its own. I didn't put the velocity here. This point P can be located using either referentials, A or B, okay? Accordingly, we have a vector position of P with respect to A that I denote as vector position of P with respect to referential A. Don't forget to put the arrow there at the top. And I'm gonna denote that, show that to you here in this figure. Okay, here you go. With respect to referential A, we have this position vector. Position vector that goes from the origin of A to point P, to the point P. And we also have this vector position from the origin of referential B to the point P, okay? On the top of that, we can also locate the origin of referential B with respect to A, and that's what this vector is all about. Well, why am I doing that? There's a reason why I'm doing that, okay? There's a reason of why I'm doing that. So watch out the notation, right? Position of P with respect to A, position of P with respect to B, and position of B, or the origin of B, with respect to A. They form a triangle. Notice that they form a triangle, all those three vectors. From this figure itself, and I'm just reminding you what we did in physics 6, okay, on relative motion. According to the above figure, there is a relationship that we can obtain from all those vectors. Okay, and here you go. Just using addition of vector, what can we say? We can say that the vector RPA is equal to RBA, okay, this vector right in here, plus vector RPB, okay? No secret here, right? You know, I just commuted them, okay? Why did I commute them? There's a reason why I commuted them, which can, you know, because when we commute them, we get this equation in a nicer way, okay? In a nicer way. In a more intuitive way. And that's the power of this notation that you're going to see, okay? So here you go. Let me zoom in a little bit more. Here you go. Notice that the point P here is the first one on the left side, right? But by rearranging those two vectors, I also get the point P as being the first on the right side, okay? Notice also that the referential A is the second on the left side. Or let's say the last one in the left side. P is the first one, A is the last one. And on the right side, A is also the last one. And now we have this nice intuitive way of expressing relative positions in which we have a repeat of the referential B here next to each other, okay? It's a very nice intuitive way of memorizing the relative position of a given point P. And it works in the other ways too, not for the position of P with respect to A, but it works also for the position of P with respect to referential B, okay? P is here in red. P is the last one on the left side, B is the last one on the right side. And whatever doesn't show up in the left side is repeated on the right side. A is not shown here in the left side, right? But it is repeated on the right side. It is as though those two can merge with each other, okay? Okay, so RP, here you go. Vector position of P with respect to B is this vector right in here. Vector position of P with respect to A is this other vector here. But then we have this vector position of A with respect to B, which is the negative of this vector that's shown here. So it's the vector that points from the origin of B to the origin of A, okay? And now, this vector plus this vector obviously is going to be RPB, Okay? And another way of expressing that too is just like writing down this equation in the referential of the point P now, okay? Position of A with respect to B, okay? Position of A with respect to P, position of P with respect to B, okay? Why am I doing that? Okay, I'm doing that because we are going to use that in the relative velocity in the special relativity, okay? So we don't have relative velocity here yet, but we can get relative velocity by, making delta R over delta P, okay? We have similar equations for the relative position, okay? So here we go. For the first equation, and it works exactly in the same way. Look at the intuitive way in which this notation is written down, right? PA, PA, PB, PB, BA, BA, and the same thing for the other ones. Okay? Let's stick with this one here. Okay? Let's stick with this middle one. And by the way, this treatment is not in the book. I like this treatment better because it helps you memorize the equations more easily. This equation that you see, applies only to Newtonian mechanics, which is an approximation to special relativity, okay? To special relativity. So the question is, how does this equation looks like? It's supposed to look like, right? To look like in special relativity, okay? Well, we can do the derivation, but it will be too much work to do that here, okay? The book doesn't derive for you. It just gives you the result, the final result, okay? Let's see if they see that he's using the same notation that I'm using, right? Velocity of the ball with respect to the ground, velocity of the ball with respect to the truck, velocity of the truck with respect to the ground. This term that you see right in here is just a term in Newtonian mechanics. And I'm going to, okay? In relativity, we have something like that, but then you have to apply a correction. And the correction that we use is this term that goes downstairs that you saw before, okay? Newtonian mechanics, special relativity. It's not much different, right? We have exactly the same term that we have in Newtonian mechanics. What is different is the term that goes below here, the denominator, the numerator and the denominator, okay? Is a number one, and a term that involves the position of the velocity of referential A with respect to B, and the velocity of point P with respect to referential A, okay? So it uses those two terms that you see upstairs. So it's not difficult to memorize. Okay, it's not difficult to memorize. See, you have VAB right in here, VPA right in here. So if I work, so right now from the bat, if I want to here write that V of P with respect to A, I already know that's gonna be V of P with respect to B, right? V of B with respect to A from that intuitive formulation. And then all you have to do is to repeat those two terms right in here. VB of A, VB of P, VP of B. The only difference that we do not have the vectors, right? Is that easy enough to memorize? Okay. If you know what's upstairs, you will know what's going to be downstairs, because the c squared is always there. The only thing that changes are those two velocities here, those two speeds. Okay. If, if VAB or VBA, if VAB is much less than C and VPA is much less than C, then the above equation returns to the original one in mechanics, right? Which is an approximation, okay? Okay, and similarly, if we, then the first, the one before the last equation, the one before the last equation, the one before the last equation returns the original one in mechanics. Similarly, if VBA is just a matter of how that the speeds, right, compare to the speed of the light, and VP of B much less than C, then the above equation return also return the above equation also returns to the original one in mechanics, which is this one right in here. Okay, let's do an example so you can have an idea of the orders of magnitude, right? Example, consider 12:42. We have 8 more minutes to go. Consider VP of A equal to 15 meters per second, VA of B 8 meters per second. Find VP of B in 2 different ways. In this case, A is the truck, B is the ground differential, and P is the ball that's being propelled. And I'm referring to this example here in the book, okay? I'm just using a different subscript, but I'm using the same values. 15 meters per second and 8 meters per second. Using the equation mechanics and using, okay, item A, mechanics, Newtonian mechanics, or Newtonian physics. Okay, let's see what's going on here. Oh, wait a minute. Oh, I'm copying from the wrong place. Yeah, here you go. Item A, this one here that I want, not the other one. Then we are going to repeat for relativistic velocities, okay? So here you go. VP over A is a positive velocity, 15 meters per second to the right side. VA of B is also positive. We have that, if the referential A measures the velocity for the ball, for the point, as being 15 meters per second, this same velocity is measured by referential B as being 23 meters per second. Okay? Faster, right? See, the guy is in the truck is moving. He's seeing a velocity he's measuring a velocity for the ball that's 8 meters per second only. Whereas, okay, since the truck is moving, this guy here that's on the ground is going to measure a velocity for this ball that's going to be 15 plus 8. That's what it is. Okay? Repeating that for relativistic, for using the formulas of relativity, because we are dealing with very small speeds. Let's see if he did that. Yeah, he's doing that. Let's see. Yeah, no, he didn't do. I am doing it. He's just mentioning it. But if you do the math, right, we do get 23 meters per second upstairs. But 8 meters per second is much smaller compared to C. Similarly, 15 meters per second is also much smaller compared to 300,000 kilometers per second, right? So when you do this math, you get this very small factor on 10 to minus 15, which is, by the way, by all practical purposes, still 23 meters per second. 5 minutes to go. The situation changes when the speed increases. When we are starting talking about relative speeds, relativistic speeds. Now consider the velocity of the ball, right? Or the point with respect to A. Velocity of the ball with respect to the truck. Now is 80% of the speed of the light. And the velocity, relative velocity of A with respect to B is 50% of the velocity of the light. Find VPB in two different ways. Okay? So we go ahead, work out the numbers for Newtonian physics, which doesn't provide you the correct result, provides you with the incorrect result. Okay, see what we're getting here when you add the velocities of the ball, 0.8 with 0.5, we get more than the velocity of the light. Okay, Newtonian physics predicts a superluminal speed, which has never been observed in real life. Whereas relativity tells us a different story that's more like we observe in real life, okay? Because of this term that we have right in here. Now, this term that you see here is going to be divided by a term larger than 1, and it's gonna bring down your final speed that you got in originally, okay? And instead of a superluminal speed, you get 93% the speed of the light. That's the important difference between relativity and Newtonian mechanics. Okay? And if we and now and then you can play with those numbers, right? Getting closer and closer to the speed of the light and see what you get. Okay? What you have to worry about the exam. Let me copy and paste the material for now that we have. 2 minutes to go. Here is the whole material for the semester for now, right? Hopefully, I'm thinking about covering another chapter next time we meet. Okay. You go. This section was covered in chapter 23. We skipped those two, right? And those are the chapter. I'm thinking about covering chapter 27. Let's see if we have time. Okay. And we do that on Monday. And then we're going to have another lab on Wednesday. Any questions? So 1 minute to go. That's all I want to cover today. And don't forget the deadline for today's lab. Turn it in on time. Okay. And I see you next Monday. Thank you for being here.
Bye, Professor.
Bye-bye.
Professor, I had a quick question.
Yeah.
Okay, so it was in regards to the lab due today. I believe lab 6.
Yeah.
So I just wanted to double check because I wasn't sure. I just wanted to see if I had done the graphs correctly, graphed them correctly. So the first graph for V1, I graphed I1 and V1. Is that the way I'm supposed to graph it?
Let's see. Lab 6,
Okay.
right? You're talking about lab
Yes,
6?
lab 6. Yes.
Okay, so
I
let's
just
go.
wanted to make sure. Okay.
Let's see. Let's go to lab 6. You have to graph V in the vertical and I in the horizontal, okay? And which group are you in this lab? Which spreadsheet group is that?
I am in group number 2.
Sure, this one here.
Yes.
Let's see if I got the right one. No, I don't think I did. This one that I want. You said number 1, right? Group 1?
No, group 2.
Group 2. Okay, let's go back. Okay, so we have V1, and let me go back to my notes. We have 3 different currents here. Let me see here what. Did you check my notes, by the way?
Yes, I did.
What
But I just wanted to, I just wanted to make sure that it was that I was graphing the correct V and then the I.
Oh yeah, it must be V1 and I1. Okay.
V1 and I1. Okay.
Yeah,
and then
right.
it would be V2 and then I2, correct?
Yeah, V2 and I2.
Okay.
And V
Okay,
total,
perfect.
I total, right?
Okay. Yes.
I total. Yeah.
Okay. And when I switched to R2 because I put 5 significant figures, so it could be 0.99, and then there's other extra numbers. What's it called? For my slope, I got instead of having a 4-digit number, I got a 3-digit number. Is that okay?
Which graph are you talking about?
Yes, I'm talking about graph number 1 for V1.
V1. Okay, so V1. Well, let's see. Is this one here? That's V2. That's V1, right? Yeah. So you're talking about the R square? That's what you're talking about?
Slope.
The slope. Oh, the slope.
Yes.
Okay, so let's put the slope here first. Add trend line, display equation chart. Okay. I'm getting and how many decimal places did you put there?
I'm getting for the first chart 909.47679.
Okay, and yeah, that's okay. You can put those numbers. You don't have to worry about significant figures. But when you get R squared equal to 1, you gotta make sure that you display a number that's not 1. Okay.
1. Okay. Yes.
So you have
for that one, I put 5 sig figs, and
Yeah.
it gave me 0.9998.
Okay, just like this one.
Okay.
Good.
Yes.
Yeah.
And so for the slope, just for the format, do you want it? For example, if it was 909.4, could I put 909, or do you want point? Yeah. Okay.
Yeah.
So-
You don't have to worry about significant figures. The significant figures here is only important right in here for R square. You never
For R square, perfect.
Yeah,
Okay.
it's only important for the R square because you never want to get an R square that's equal to 1. Okay.
Oh, okay, perfect.
Never
Thank you so
wanna
much,
get-
Professor.
Okay.
Okay, that was my question. Thank you.
Okay.
Bye.
Right. So, Jahusa, are you there?
Yeah.
Okay.
Quick question.
Yeah. How can I help?
For exam 3, number 8, I was wondering if you could explain that very quickly to me.
Sure. Let's go there. Number 3. Am I sharing the screen? No, not sharing the screen. Okay. Physics 38, spring 30. Physics 38, spring strange. I have two. What's that? Okay, I'm in the wrong place here. Okay. So many windows, we end up lost here. Now let's go to exam 3, great. And Jatusan, right?
Yeah.
I don't see here you in your, no, Jatusan, your first name. Okay, your last name is Vima. Vima, let's roll 1. Now let's get this one. Speed grader. Question number 8. Oh yeah, okay. Okay, I did this one with another student just recently. This is an interesting problem, okay? Question number 8. Okay, so let me get also my PowerPoints. Exams, let's see here. Attendance, welcome letter. Homework solution, maybe this one here. Yeah, this one I solved for a student that came by last week. And last week, no, Monday, right? So let's do it together. Let's do it together, and let's see if I can get illustration. I'll get my illustrations here. Okay, this one here. Let me share the screen with you. Okay, so here you go. It's not exactly the same drawing, right? But let me, we have let's start with the line, right? Carrying a current that varies in time, right? So that's the first what we have here is a current that goes from the right to the left. I. Okay? That's the first frame of my movie, right? That's the first frame of my movie. In my next frame, I'm going to have this circuit here. That doesn't have any power source whatsoever. It's just a closed circuit. It has no battery whatsoever. This line here has a battery somewhere, okay? That's why we have a current flowing through that. Right. And I have the dimensions for this for this is a square for this loop. This, this wire is not in electrical contact with the other wire. Okay, that's why he drew like that with this little curl. Okay, this little curl here means that they're not making contact. I didn't want to make the curl because it would be too much. Okay.
Yeah, right.
Okay, so what's next? Okay, this current is changing in time. Because this current is changing in time, the flux, the magnetic flux through this loop is also changing in time, right? Do you agree with that?
Yeah.
Okay, and there is more. Here at the top, okay, the magnetic field is going to point in which direction does the magnetic field points at the top of the wire. A question that I'm making you, right? Here you go. Do the right hand rule.
It would be towards us?
No, it's not
Towards the
towards.
page?
Okay, well, it's either towards or away, right?
Yeah.
Okay, there's no. If you miss the first question, you know what's the or what the actual answer is, right?
Yeah.
Okay, so just do the right hand rule, right? The thumb points in the direction of the current, and you curl your hand. Okay, so it's gonna the magnetic field is gonna point towards you, right? Away from the screen. So I'm going to fill that in black. Like that, right? Just the tip of the arrow illustrating the tip of the arrow illustrating the direction of the magnetic field.
Right.
Right? So here you go. It takes time because I'm doing with PowerPoint, right? If you were to do by hand, it wouldn't take as much time. Okay, and now what's going to be the direction of the magnetic field on the bottom part, on this bottom part here? Do the right hand rule again, right? What do you get?
I'm not really good at that. I always mess it up.
Yeah, you gotta do it. You gotta learn, right? You gotta learn, otherwise you won't do well in the course, right? Point the thumb in the direction of the current and curl your hand, right hand.
Yeah.
Right. So the on the lower part of the loop, the magnetic field points. Points into the board, right? If the one is away from the board, the one below is into the board. Here you go, right in here.
Okay.
Right? Now you know how the magnetic field works. You can start calculating, having an idea how the flux goes, because it's going to involve the flux, right? The magnetic flux. Oops, not this one. Oh gosh. So let me fill everything here. Like that. Okay, here you go. That's the magnetic field. away from the screen into the screen. Okay, what else do we need? Okay, now we need to start doing the calculations now, okay? You already know what's the equation for the magnetic field of the wire, right? What's the equation for the magnetic field of the infinitely long wire?
Hold on.
We calculate that.
Do you apply Faraday's law to this?
Apply what?
Faraday's law?
Faraday's law. No, it's not Faraday's law. It's Ampere's law. Okay. The problem applies. The problem this problem here uses Faraday's law. Yes, but if you want to find out the magnetic field due to the wire, you have to use Ampere's law. Okay.
Okay.
The one with the path integral, B dot dl, closed path. Okay.
Okay.
And let me show you if you don't remember. Okay, that's the current, right? The current is changing like that.
Okay.
Back here, the current is 6.2 t squared, 10.3 t. Okay, minus 10.33. The magnetic field of a long wire is this one here. We calculated using Ampere's law, mu naught I over 2 pi r. Do you remember that?
Okay, yeah.
Okay. So, and now you get the I that changes as time goes by. You plug it right in here, and that's exactly what I did. Okay. Exactly what I did. Okay, now we have the magnetic field. Now that we have the magnetic field, we have to calculate the magnetic flux. Okay? The magnetic flux. With the magnetic flux, we are going to determine what's the electromotive force that is being generated at that closed loop at a given instant of time. Okay? So here you go. That's the magnetic flux, right? We still do not know what the limits of the integral. So I put the question mark here. We will find out, but we will find out, okay? I substitute the B here, mu naught I 2 pi r. We are integrating in the n, okay? The only term here in this equation that depends on the A is going to be the 1 over r, okay? That's the only term. Okay. Everything else is independent of the A. That's why I put it outside the integral, okay? It doesn't matter that the I is a function of time. It doesn't matter. It doesn't. So we still can take it out of the integral because we are not integrating in time here. Make sense?
Right, yeah.
Okay. So here you go. And then what do we do next? We have this dA, right? In this dA, we have to come up with a way to express the infinitesimal area in terms of the known variables, okay? In terms of the known variables. And then we have to go back here to this graph. I'm gonna use this one here. Okay, so here you go. I'm gonna use, here is the coordinate r that goes from the infinitely long wire to somewhere, to a place somewhere here in this loop, right? Make sense? And then what else? Okay. What else am I going to do? I'm going to depict the infinitesimal area at this position. I'm going to depict the infinity, and then that's how I do it. I draw this rectangle, okay? That has a side B and another side that is equal to dr, right? Here you go, dr here. Let me get another, let's see. Yeah, okay. I'm gonna get another one. dr. Here you go, right? That's the infinitesimal area that we are talking about.
Mhm.
The infinitesimal area that we're talking about is B times dr. And now what was supposed to be, what was initially, not supposed to be, but what was initially a double integral becomes a single integral. Make sense? Right?
Okay. Yeah.
Okay, so now I replace dA with B dr. And now it's easy to calculate this integral, right? B is still a constant, right? We can take the B outside the integrand, and then we are left with this integral. But I still do not know what the limits of this integral. I still didn't discuss with you what but at least we know that how to calculate this integral. This integral is easy to calculate, right? The integral of
Okay.
that this one is easy. Now we have to think in terms of the limits of this integral. Okay?
Mhm.
So we're going to have two magnetic flux of different signs, right? The flux here at the top is going to be, let's say this one is positive, and this one is going to be negative, right? Whatever, the flux, this flux here is going to cancel part of this flux here in this lower part of the loop. Do you agree with me?
Okay.
Okay. So if you had, if your loop would ended up only here, if that were the loop, then the total flux through this loop here would be zero, right? Because the magnetic flux here at this lower part in this region here will be the negative of the magnetic flux in this upper part. Don't you agree with me?
Yeah. Okay. That makes sense.
Okay, so I can, in this case, I just shrink it, right? Just like for the sake of illustration. Okay. In this case, let's see. If here is A, and here is A, so I got to stretch it a little bit more. Like that. The magnetic flux, the net magnetic flux through this area would be zero because, right? The magnetic flux through this whole area would be zero. But that's not the case, right? The case that we're doing is this other one here. The net magnetic flux is not going to be zero. The net magnetic flux is going to be what we are going to calculate now. Okay? And what else does he tell us? Okay, he told us this one is A. Okay? So let's A, right? Okay. This one, let's see. I'll put it here. Is this one in the right place? I don't think it is. Okay, this one. Yeah, leave it here. Leave it here. Now we're going to do the actual calculation, right? And we're going to get the limits that we're going to do. We're going to find the flux here, and we're going to find the flux here. Okay?
Okay.
So here you go. And that's the integral that we want to calculate. Okay? I'm going to write it down. Okay. Here you go. We're actually going to get two different integrals. One going from 0 to b minus a, positive, right? Positive because the flux here is positive. From 0 is the distance from the r is the distance from the wire, right? At the wire is 0. At the top of this loop is b minus a, right?
Yeah.
I'm gonna label here. B minus A. B minus A. Let's stretch a little bit more. Yeah. So I solve the flux to this upper part here. Right? Now I've got to solve the flux for the lower part. The lower part is going to be from 0 to A, but it has to be negative, right? It has to be negative because the field is pointing the other direction. That's why I put this negative sign here, okay? From 0 to A, right? That's the integral that we're talking about. Let me highlight it here. And then I'm going to highlight it here. Highlight it here. Okay?
Yeah.
Okay, what else can we do? But there is one more step that we can do to simplify this calculation, okay? We can break down this integral into two other integrals, okay? An integral going from 0 to b minus a, just like I have b minus a here, right?
Mm-hmm.
And another integral that goes from b minus a to a, right? That's what this integral is all about.
Okay, yeah.
I'm going to put it here. But, you know, is equal to but, you know, but is equal to this plus this b minus a to a, okay, like that.
Okay. Yeah.
And then, you know, instead of writing like that, I'm gonna write it downstairs. Okay. Right? Now compare this term with this term, right? They're exactly the same with the exception of a sign. The limits are the same. The integrand is the same. Even the multiplicative factor is the same, right?
Yeah.
So we can cancel that out. And there you go. You can cancel it out to get that. Now we can apply the limits. We can, you know, find the integral and apply the limits, right? The integral is going to be log of r. Limits is b minus a to a. And then that's what you get here. Okay? We found the flux.
Yeah. Okay.
Found the flux. Here you go. The flux, I didn't write down the flux yet. Oh, the flux is here. Why did I repeat that? I shouldn't have repeated that. There's no need to repeat that. Let me erase that. Oh, I think I know what I meant. I meant to put this term here without the limits, okay? Yeah. Now I know that this term here is a function of time. Let's not forget that. Let's not forget that. This is the term that's going to induce a current or is going to induce an electromotive force in the other circuit, right? Which is given by the differential of the flux in time. with a negative sign here. Okay. So everything else is a constant. The only term that's a function of time is the current. Okay. And then I take the differential, right? The derivative. Okay. And I get that. That's what I get. Note that the electromotive force is changing with time. Okay? Make sense? It's changing with time. And there is more. The book didn't tell, but this number here has a unit. The unit is amperes over second square. Let's see if I put the units there. Yeah, I didn't put the units there. But that's common, or not using the units there, okay? Treat everything as though it has no units. Okay, so that's the equation for the electromotive force. What is he asking? He's asking the electromotive force at time t equal to 3.12 seconds. Okay? So all you have to do is to calculate the electromotive force at this instant of time. And let's see, I think I did that here too. Let's see if I can find it. P07, 238. This one. Must be this one. Yeah, this one here. Okay, A equal 0.159, B, right? 0.218.
Yeah.
Okay, meters. I'm writing that in meters. 3.12 seconds, and then I wrote down the equation. I wrote down the equation of the electromotive force. Okay, and substitute all the numbers, and then what do I get? 1.22 microvolts. Okay, 1.23, right? Microvolts. And you put 2.46, right? You for some you came up with the double. See that? You put the double value. Most likely because you didn't subtract, one from the other. Maybe, right? How do you?
So I'm trying to look at.
Yeah. You did that?
I think no, I did subtract. I think there's something else. I think something wrong with using natural or not natural log, but log. Somewhere where I don't know, for some reason multiply by 2.
Yeah, I don't know what you did. Do you have your paper, that you did your calculation?
No, I do not.
Yeah, it's always good to check to ensure that you don't make this mistake again, right?
Yeah, no, I just assumed I was completely wrong, but I was somewhat in the ballpark. But that makes sense, though.
Yeah, that makes far more sense, right, when we do it this way, right?
Yeah, this is okay. I get it now. Okay. Thank you. That helps.
Anything else?
Yeah. No, that's all I had.
Okay.
Okay.
So see you
Have a nice
soon.
day. Yeah.
And by the way, I have the date of the final exam, right?
Yes.
Let me see if I
there.
have the date of the final exam here. We're coming to the point where we have to start worrying about that. Final exam, 3rd of June. Yeah, 3rd of June. 3rd of June, is that right?
Yeah, June 3rd, due June 4th.
Aren't we supposed to do that on June 6th? I hope I didn't make a mistake here. But it's okay to be on June 3rd, right?
Yeah.
Let's see. I suspect class schedule. Let's see here. Yeah, I gotta stop recording.